Hey guys, this is it. We've made it here. Our first lecture that's going to talk about hypothesis testing in a way that leads us to actually testing hypotheses. That being said, I want to review standardization stuff first because it's really important to your understanding of how hypothesis testing works that we remember how things like this normal distribution can represent any variable at all as long as we standardize it, right? So we place it in this sort of standardized world. So far we've talked about z-scores and z-statistics being the way to do that. I'll show you another one later on, but it's basically through that mechanism that we allow raw data to take on this perfectly normal form. Remember the central limit theorem, as long as our sample size is large enough, then that distribution of sample means, that's the standardized distribution, will look normal. And that means that we know exactly what percentage of the distribution falls within various cutoffs, right? So if I say start at the center, where we know the standard score of that distribution, the center of the distribution will be 0, right? The average of the distribution will be 0 standard deviations away from itself. But if we go one standard deviation out, you can see we get up to 68%. Right? We go another standard deviation out, we add another 28%. We now have the vast majority of the population within 2 standard deviations above or below the mean. In fact, beyond 2 standard deviations, there's really only about 4% of the entire population, which means if we found a sample that was 2 standard deviations above the mean of that entire population, we can say that's starting to look pretty unusual, right? That's something that's way above the mean, or 2 standard deviations below. And it's that logic, that rationale, that allows us to perform hypothesis testing. So let's see what kind of things we can do with standardization, right? We've seen percentiles already, so let's go through an example. Let's say we have a young girl named Jessica. She's 15 years old. We measure her height precisely at 66.41 inches tall. Now, I went to the CDC website to figure out how tall 15-year-old girls are supposed to be. And according to the CDC, the average height of 15-year-old girls in the United States is 63.8 inches. Okay, so Jessica's 66.41 inches. The question is Jessica really different from that population? And if so, how different? Well, we are provided both with the population average, and the CDC gave me the population standard deviation. Thank you, CDC. This means we can calculate a z-score. Right? In this case, it's just a z-score because we're seeing where Jessica, an individual, lies within the population. If we're looking to see where a sample lies within a population of samples, then it's a z-statistic. Basically calculated in almost the same way, though. So in this case, z is equal to x, that's her score, right, 66.41, minus the population mean of mu, 63.8, divided by 2.66, this is just the z-score formula. We get a z-score for Jessica of 0.98, saying that her height is about 1 standard deviation above the mean. Right? So if we look then at our z-table, and this is the one from the back of the book, we can go over to the left and see where you go all the way to 0.98 and then carry it over to the right and see that that says that the percentage between the mean of the distribution, that 0, that center line, and where the z-score is, right, wherever it happens to be, this table's just telling you the percentage, is going to be, in this case, 33.65%. So if we visually think about that, draw this distribution, and I encourage you, please, draw the distribution for every single problem where we have to do one of these until you feel like it is no longer necessary, because it will help you. It will almost never hurt you. Okay, so I draw the distribution, I leave it blank, draw a center line, label it 0, and then I say, okay, her z-score was 0.98, so about 1. So I go to the right a little bit, draw a line. It doesn't matter if that's precise, right? This is just allowing you to think about the percentages. And then we see that our table tells us that 33.65% of the population fall between that center line and that that z-score line. So we can write that in, shade it in, and say roughly 34% here. Well, because that's a positive z-score, we also know that there's all that space below 0, right? The other half of the distribution, so the other 50%. So when we think about percentiles here, we would say that Jessica is in roughly the 84th percentile, right? 83.65% of the population falls at or below Jessica's height. Well, if 83.65% are the same height or shorter than Jessica, how many are taller? Well, that's easy, right? We can just do 100 minus that 83.65. Or if we started from scratch and we had our 33.65%, well, we know that's just on the right half of the distribution is 50. So we can do 50 minus 33.65. I don't care how you come up with it. Either way, you get to the answer of roughly 16.35% of the population then being taller than Jessica. Okay, this exercise, and we're going to do another one as well, is just to get you familiar with looking at these distributions and working with your z-table so that you can see how different standard deviations above or below the mean correspond to different percentages that are either above or below that score. One more, actually, so wrong direction. If we can figure out then, let's say Jessica is this far above the mean, right? She's this extreme perhaps, right? Can we say how many people are a similar level of distance from the mean, but in the other direction, right? And so in other words, how many people are that far from the mean in either direction, right? How many people are that unusual, if you will? In this case, because Jessica was at roughly the 0.98 standard deviations above, we would say the same thing for the 0.98 below, same cutoff, right? And we're asking what those two tails represent. Well, we already calculated the tail in the last example, so we know it's 16.35% above Jessica, which means if we had a negative z-score, there'd be 16.35% below that z-score as well. So combined, you get a 32.7. So roughly a third of the population is that different from the mean, right? The same level of different from the mean that Jessica is. Let's go through another example. Different individual, just to really make sure we hammer this home. Manuel is 15 years old. He's 61.2 inches tall. For 15-year-old boys, we have a mean of 67 inches and a standard deviation of 3.19. Again, this is given to us by the CDC, so we can treat these as population values. We calculate Manuel's z-score, and because Manuel is below the average, and it looks like considerably below the average, his z-score works out to be a negative 1.82. So again, we fly back to the z-table and we look up what that value is. Remember, the z-table is only going to give you positive z-scores because the distribution is symmetrical. A negative 1.82 is going to be in the same position on this side of the distribution as a 1.82 would have been over here. Okay, so you look that up and then you just write it on the negative side of your little distribution. So 46.56%. Let's draw our curves. All right, we got a big ass normal distribution curve. Draw your center line for 0 and say, okay, Manuel had a negative 1.82, so I'm going to go to the left. I'm going to draw a line for his z-score. Now I'm going to look up in the table, and it said to me that there was 46.56% of the distribution between the 0 center point and that negative z-score. So if we're talking about percentiles, we want to know how many scores fall at or below Manuel's score, Manuel's height. So in this case, we would want to find out that tail end. So we can take the 50% that we know represents that whole negative half of the distribution and subtract off the 46.56% that we know lies between the center and that negative z-score. Right? That will leave us then that little bit of the tail, that 3.44% that remains. So Manuel's percentile is a little under 3.5, so he's in the third percentile, meaning 3% of the population is as tall or shorter than Manuel. Well, that would mean then that roughly 97% of the population is taller than Manuel. So now we're starting to see that in Manuel's case, his height is a particularly unusual event if roughly 97% of the population is taller than Manuel. Now we can talk about, just like before, what percentage is as extreme into the tails as Manuel. Well, if 3.44% is farther than him into the tail on the negative side, it'd be the same thing as the positive side, and we'd end up with roughly a 7% of the population being as far from the mean as Manuel. As extreme, as this guy's messed up tattoo says, from the population as Manuel. All right, so this is where we're going to start using this for population, or for hypothesis testing, because we want to say, is the difference between our samples, or is the measurement of this one individual sample far enough from the population mean that we can say, there's no way this happened just due to chance, right? It's so unlikely. If only 7% of the population is as extreme as Manuel, finding an individual like Manuel would be an unusual event. Finding a difference like this in an experiment would be an unusual event if we think this represents all of the likely events, right? And so it's this kind of philosophy that we're going to use moving forward to approach hypothesis testing. Remember, we can talk about this as probability as well. So what's the probability of being shorter than Manuel? Well, Manuel was at that negative 1.82, so we can talk about it either as his height, the probability of a raw score being less than 61.2 inches, or the probability of a z-score being less than 1.82, in this case, negative 1.82. We've calculated that, right? It's just the 3.44%. It's just how many individuals are shorter than Manuel. Right? We could do the other side as well. What's the probability of the average of a sample, right? Or the probability of an individual being greater than 61.2. It's just going to be the counter of that, right? So 96.56%. We can also go from percentages to z-scores, or from z-scores back to percentages, right? Something you'll want to get used to doing because it allows you to really get comfortable with that z-table. So an SAT example. Let's say, and this is actually, again, from Educational Testing Services, the mean on a particular subtest of the SAT is 500. The standard deviation on that same subtest is 100. This is because that is standardized to be that way. So you take the SAT. You're applying to colleges, you go take the SAT, and the SAT reporting service, ETS, decides they're going to really test your knowledge. Instead of telling you your raw score, they're going to tell you the population mean was 500, the standard deviation was 100, you are in the 63rd percentile. Well, you know that you beat out 63% of the population, right? Because our 63% is either at or below your score. So visually, draw that distribution again, put the 0, put the z-score over here at 0.33, which we're going to look up here in a second. But we know that that would be where you would be for the 63rd percentile, because 50% of the way through, you're an additional 13% of the way through, right? And so that's the number we have to look up. Remember that the way our table was working is we look up the percentage between the mean and the z-score. Well, 50% is on the other side. 13% is between the mean and our particular z-score, because we know that based on 50 plus the additional percentage. So we can then go into the table with that 13%. Okay, we have to find the z-score corresponding to 13%. So we do that fairly easily, right? We have to scan through the table a little bit, try and find the one that is closest to that value. You'll notice in this case there's a z-score that corresponds to 0.1293, and another one next to it that corresponds to 0.1331. One of them is slightly below 13%. The other one would be slightly above 13%. In this case, because we're trying to find the z-score that represents this individual's percentile, we want to be conservative and not round over 13%, and instead round slightly under. So we're going to use the 0.1293 value, okay? So then if you look to see what that z-score actually would be, the 0.1293 corresponds to a z of 0.33, right? Just like we had seen on the actual distribution that was drawn earlier, a z-score of 0.33. Okay, so we're almost there now. We've got our percentage. We figured out our z-score. Now can we figure out our raw score? What score did we actually get on the SAT? Well, that's easy enough because we can simply rewrite our z-score formula, right, to solve for x instead of to solve for z. And then we plug in the values we know. We have a population mean, we have a population standard deviation, and we just looked up the z-score. So plug it all in, right? The equation should look a little like this, solve through, and we get an x of 533. Okay, so what I want you to do, if you haven't already, is go look at the homework for this section. It's on this exact information. You're going to go back and forth between percentiles, z-scores, raw scores, really just getting some familiarity with your table. So look at your most recent, or well, depending on when you watch this, Canvas announcement that's got an attachment for that Z table, okay? It's also there on the main page for this particular unit. You can also find it in the files section in case you missed the announcement. But get comfortable with the Z table. Do lots and lots of problems. Find some extra ones in your book or online, because this is going to be one of the easiest sections on the next exam, and it's somewhat fundamental to the way that we approach hypothesis testing, that you understand this process. Okay, so it's sort of a win-win if you go and practice on this one. Plus, they're pretty easy. So do that, then watch the next video. All right, cheers.